All right. Hello, everybody. Welcome to EC 5234. This is a communication theory class. This semester is spring 2012. And here's what you have in your hands is the outline of the course. So at the beginning, let me go through it to make sure we scope the course properly and understand what is going to be covered and how you guys are going to get a grade in this course. First thing first, my name is Ivica Kosnić, that's at the very top here. Here's my email address, and below that is what you will find probably the most important part of this introductory information. This is a website where you're going to get a whole bunch of material related to this class and other classes that I teach. If you go there, you will find out all the lecture notes that are essentially content of the notebook that I'm teaching from. You're going to find some sample problems. You're going to find whatever auxiliary material I post for this course. Also, starting as of this semester, we're filming these classes, so there you're going to find out the video recordings of the classes that you have here. And this is done for several reasons. One is to maximize, I guess, the usefulness of me presenting this material, because nobody catches everything when they see it first time. But also, a lot of you travel and for whatever reason may not be able to attend the class, or the class is going to be there and, all the time. My office is in All Engineering Building, room 304. For the summer semester, I'm going to be holding office hours every Tuesday and Thursday between 4 and 5:30. I didn't put that on this syllabus because I plan on reusing this for other semesters in which office hours are going to be different. There's also a phone number there, but either use email or just come, because the phone sometimes works, sometimes it doesn't. So it's a kind of archaic way of communicating anyway. Here are the two books that I'm going to be using for this course. One is this Communication Systems by Proakis, and it's one of the classic books. It's available, universally. You can get it at a relatively cheap price if you buy it used. I think you can get it like for $20–30. The next one is this supplementary book. And this is called Analog and Digital Communications, and it's a book that contains nothing but problems. Right? Teaching this course, what I've realized is it's all about problems and your ability to solve different problems. There's one thing in understanding theory, but it's far, I guess, more important, and kind of the level of knowledge that you need to have is ability to solve problems. And what I find out is they're not necessarily one-to-one correspondence. I found students who went through all the theory, but when facing problems, they didn't know how to solve it, right? So this book is going to be a supplementary book. I'm going to be using it extensively. There's 333 fully solved problems. And there's also a whole bunch of other problems that are not solved. And I will be, assigning problems from here, doing some of them in the class, and using this book to form my midterm and final exam. Right? So just make this book your friend and your companion, and try to use it as much as possible, because that will pay off. The next thing that you have here is the section that contains all the lectures, right? And I kind of try to spell out what I intend to cover in any given class period. And you can see just from the outline, it is a standard course in communication. The purpose of this course is to bring everybody to the same body of knowledge so that you can take more advanced courses. Some of you might have seen some material as undergrads. Some of them are new to this material. But my hope is at the end of this course, everybody is proficient in these things that you have here. And topics are important on their own, but they're, I would say, more important from the standpoint of the tools that you need to master to get these learnings, right? So for example, when I'm covering here Fourier transform, it's not so much that you've never seen the Fourier transform, probably you did, but the emphasis here is to make sure we understand what it is, what it's used for, and how it relates to the task that we need to do in the communication systems. So when you do these problems, always think about what is it that we're actually doing here? What do they mean for us? I mean, there's mechanics of it, and I appreciate the mechanics. You have to have the mechanics to execute and solve problems, but understanding it of what we're doing is also a very important concept. One thing that you'll notice going through these classes, there are several classes that are dedicated to just problem solving, right? I typically have a couple of them throughout the semester where I prepare you for midterm and finals. This time I'm actually throwing in, I think, 4 lectures where we're going to be doing nothing but problem solving. And they're kind of spaced strategically throughout the course to exercise certain sections of the course. My advice is, before we get to this problem session, I'll always have prepared problems that I want to solve. But my advice is, anything that you encounter in between these problem solving sessions that you would like me to address, please bring it, and I'll take that as a priority. I'd rather address your questions than do my own, right? Because my own are going to be documented, you're going to find them in notes anyway. But the things that you have stumbled when you're doing problems from here or problems from this book or in general are going to have priorities. So that's the first 2 sections. The third one is there's 3 components to the grade. They're going to be homework assignments, and they're going to carry 30%. There will be a midterm exam with a 40% and the final exam 30%. So just the standard, approach that I have in pretty much every one of the courses I teach. And the last point is the grade. This is a standard grade scale, so make sure you fall between 90 and 100, and that's your rate. Right. I have put an additional note here. Many of the students tend to select this course for their master's comprehensive exam, and when they select it, maybe a month before the exam, I have a whole bunch of them come to my office asking me what is going to be on the exam. I have put some guidelines here, but essentially every example and every problem that I did in the class, along with the ones that are coming for the homework assignment, are the pool of examples that I select for the comprehensive exam. I have to be realistic because the exam is 1 hour, so I cannot select the most difficult ones. But I'll give you a secret. What I do when I prepare these exams, I take some of these problems, change some numbers, wordings, but they're essentially the same problems. So if you know the problems that are coming from this book and that are done in the class and for the homework and examples, you're good to go. Now that seems easy, but there's going to be a lot of problems. So my confidence is, if you know all of these problems, you're pretty prepared and you're ready to pass. Right? So that's pretty much what's on this sheet. Any questions before we start? Go ahead.
By the time we get up to the session 1 for problem solving, will that be by Thursday or next week?
It's going to be Tuesday next week if we execute in accordance to this plan. Right. Oh, one thing I need to note here. This is a summer class. It's an 8-week class. So it requires a lot of effort. It's not, hopefully this is the only class you're taking, right? It's not like the classes in the regular semester where everything is spread over 16 weeks. Here we have an 8-week schedule, so there's going to be a lot of it covered, during a period of 1 week. So plan accordingly, plan a lot of time to study, right? Because the material is very compressed, and but that doesn't change the amount of material that we need to cover and the level that we need to reach throughout this course. All right, so are any other questions? I guess none of us is new to school, so this is another one of the classes, so let's go through the material. I'm going to start today with some introductory remarks. First, we're going to review the outline of the communication system, and then I'll talk about, in particular, more about communication channel, and not so much about the physics of it, but the mathematical models that we're going to use through the class to model communication channel. So here's a block diagram communication system. Let me draw it and then we'll discuss various components. So usually you would have some sort of information source. This is the entity that generates information. Good example would be me talking here. And then you have the next block, which is transmitter. Then we have something that we call communication channel. We have what we call receiver here. And then we have information sink. Okay, so that's a block diagram of a general communication system. The purpose of the communication system is to take the information from the source and deliver it to the sink. Now, that's easily said, but that's actually quite complex statement because of the how much difficulty we have in defining what the information really is. Even let's say transmitting something to the other side may carry less of information if the other side already knows, right? I already heard it, so there's very little information even though we went through the whole trouble of transmitting. So in this course, this notion of information and although very important, is not going to be addressed in this course. We're going to actually narrow down what we consider a communication system and kind of look at only this piece here. We're not going to be concerned about information per se. We're actually going to look at these three blocks here and assume following, that we are not translating information from this side to this side, but instead we're concerned of sending signals from one side to the other. There's a difference because a signal may carry or may not carry information, but whether it does carry information is outside of the scope of this course. We're going to have some signals coming in here, and we would like to reproduce these signals as they come at the output here. So what is, so I'm going to say here there's a signal at this point, and there's a signal at the output. Now, how are these signals generated? Well, signals are essentially in our world voltages and currents. The information itself, or what we're trying to send to the other end, does not come as a voltage and a current. When I speak, it's an acoustic wave. When we're being filmed, that's a moving image that needs to be somehow captured and translated into a signal. So, big part of I guess, information processing here is what we call transducers. So there's an input transducer that is responsible for translating information into signals. What are some typical examples of the input transducer? Your microphone, right? Microphone takes the acoustic wave and makes it a voltage. Your camera takes this image here and translates that into a whole bunch of currents and voltages. Your keyboard, it takes, your, I guess, words and what you're trying to type and translates that into voltages and currents that are further processed by the computer. So our output in our system is input into our system is the output of the transducer. It's already voltage and current. The next block in this diagram is the transmitter. The purpose of the transmitter is to accept this signal from the transducer and adjust it so that it can be sent over the communication channel. The signals that are coming out of the transducers are typically what we call baseband signals. There are voltages and the currents at the low end of spectrum. When I speak, do you know what are the frequencies that are in my speech signal? If I were to look at this signal here, what is it made of? Do you know what's the bandwidth? Well, we're going to learn it, but it's up to 4 kilohertz in a telephone voice. You can, and if let's say I want to send that to a cell phone to a tower, can I transmit at 4 kilohertz? No, because it's such a low frequency. The antenna that I have, that I would have to have, would be like several kilometers big. So there is a block diagram here, or part of the communication system that will accept these baseband signals, do processing with them, and then adjust them so that they can be sent over the channel. If the channel is optical fiber, then it needs to translate this into the light and so on. So I guess it adjusts the properties of the signal so that it can be sent over the channel. Now, this adjust the properties is a loaded term here, because it does a whole bunch of things. If this is a digital communication system, transmitter will digitize your signal, perform the error control coding. It would modulate the carrier, up convert, down convert, amplify, do a whole bunch of things to adjust the properties of what is being sent here, so that it can be, it can actually go through the channel itself. So I guess depending on, on the signal and type of the communication system, transmitter may sample, quantize, encode, filter, amplify, and so on, right? We'll lose some of these tasks when we start talking about modulation, demodulation, and so on. So these are these first two blocks. Let's take a look at channel. What is a channel? Channel is a physical medium that is used for transmission of signals between transmitter and the receiver. So it's a physical medium. Used for signal transmission. Now, there are several types of channels. So let's kind of go through a list and try to survey them a little bit. So if I say communication channels, there are two major types. There is what we can refer to as wireline, and there's what can be referred to as wireless. There are wireline channels and then wireless channels. If you're talking about the wireline channels, you can have electrical and then optical. Electrical wireline channel or optical wireline channel. What are typical examples of electrical wireline channel? There's something called twisted pair. Do you know what twisted pair is? Is that those two cables, that blue and white one that are in every one of the telephone, landline telephones. So, for example, twisted pair, coaxial cable, waveguide, and so on, right? As far as optical wireline channel, these are your optical fibers. And those are, the main channels that are kind of running most of our large-scale communication networks. Entire internet, landline telephony, voice and data all runs over the top of the optical fiber communication channels. Now, wireless, we have three types. We have RF channel. These are your EM waves. of the RF portion of spectrum, which is, let's say, 3 kilohertz to 300 gigahertz. That's where the RF spectrum will reside. Then you have optical wireless channel. These are your communications in infrared. What would be a device that would use this kind of channel? Very popular device. Laser. Okay, laser. Another one even more popular. Remote control. Don't forget remote control. And then there is another one which is acoustic, right? Now, both of these, RF channel and optical, they're both using electromagnetic waves, right? It's just different frequencies. This is a lower frequency band, and this is a higher frequency band. Acoustic wireless channel is different. It uses acoustic waves. What is the example of acoustic wireless channel? Underwater is a prime example because of underwater propagation of electromagnetic waves is just limited to a few wavelengths, so you have to use acoustic wave. Even more obvious one is this one. When I'm talking to you, we're talking wirelessly, and we're talking through acoustic communication channel. Right? So these are all different channels, and just a high level, division between them. You can actually look at each one of them individually and kind of find out a whole bunch of examples. And they're all going to have different physical properties. And on the outset, it seems pretty daunting just to deal with the wireless channel. And indeed, we have some courses, for example, wireless propagation, that deals only with wireless communication channel because of its complexity, right? But from the standpoint of this course, we're not going to go into that great of detail. What we're going to do is we're going to derive mathematical abstraction for all of these channels. We'll see how we can model them mathematically. And then, later when you try to use all of this theory, you're going to say, okay, this is, for example, electrical twisted pair channel. This fits into this mathematical model. These are the parameters of the model, and you'll know how it will impact the communication system. Now, one of the biggest, or one of the most significant properties of the channel is that it distorts the signal. In other words, what you place into the communication channel and what comes out of the channel are not going to be the same things. That's universally true for all of these channels. They're going to change your signal. There are typically two ways how the channel can change. The change in the signal we're going to refer to as distortion. So the channels distort the signal. There are two ways how the signal can be distorted as it propagates through channel. So let me put that here as a note. The channel distorts the signal. And there are two ways, two types of distortion. First type we're going to call additive distortion. And the second type we're going to call that non-additive, right? When we talk about the channel models, we're actually going to address these in more detail and see for a given model what types of distortions it will introduce, so that hopefully I'm just going to leave this right now undefined, and then when we go through the channels, we're going to talk into more detail what type of distortion does each one of them introduce into the signal. Now, the last two blocks is this receiver here, and of course there will be another transducer here. So let's talk about the tasks of these two. So RX stands for receiver. The purpose of the receiver is to accept this signal here. Now that is a distorted version of the original signal, and then try to recover what has actually been sent, right? So it's a very complicated task, even on the outset. You can see that channel may be more or less complicated. It can distort the signal in many different ways. And the receiver is the one who needs to cope up with it. It needs to actually look what it has received and try to recover what it has been sent. So in majority communication systems, the receiver is the most complicated part of the system. There's great deal of I guess engineering that goes into the receiver, and it kind of in a lot of communication systems it becomes to the point where some of the things that the receiver does need to do. Actually, there's some of the part of the transmitter design are actually guided by what the receiver needs to do. So the transmitter does a lot of processing so that the receiver has an easier task at the other end of the communication system. So I guess purpose is receiver accepts the distorted signal and tries and performs, I should say, its recovery. And as I said, there's a lot of tasks that it needs to do. We'll talk about some of these tasks. But in essence, whatever transmitter does to the signal, the receiver needs to undo. Whatever the channel does to the signal, receiver needs to undo, so that whatever came into this system, hopefully something very similar comes at the output of the system. And the last here portion is just the same comment as I had earlier. You know, the information that's generated in what is called native form is usually not the voltage or current. You know, when I speak, it's an acoustic wave. So I cannot take this acoustic wave, translate it into voltage, and then just present the voltage at the output. We need to convert this voltage back to the acoustic wave. And there is a block here that is usually in the communication system for that purpose. In the case of acoustic wave, you have a microphone here that does conversion from acoustic wave to signal. You're going to have a speaker here that is going to take the signal and make it an acoustic waveform. If you have a camera, on one end you're going to have some sort of screen on the other end, and so on. So there is always an output transducer. Converts signal into the native form for the information. Any questions about any of this? Okay. So let's now spend some time on a channel and derive some of the mathematical models for the channel. And that's kind of all the time that we're going to dedicate to the channel. Channel, as I said, is a relatively complex subject of this whole picture. But in this class, once we go through the mathematical modeling, we're going to use the models throughout the rest of the class. And we're going to focus on what is done by this block and what is done by this particular block. So let's talk about mathematical models of the communication channel. Mathematical models of communication. Okay. So there are several mathematical mathematical models. In this class, we're actually going to restrict our attention to 3. Right? So we're going to consider 3 mathematical models. 3 models. We're going to give them following names. An additive noise channel. The second one is going to be linear time invariant filter channel. And the third one is going to be linear time variant filter channel. So these are the 3 types of channels that we're going to consider. Let's look at first the block diagram of the additive noise channel. This is how this channel looks like. You have your signal, so this is the same signal that comes into the channel, the output of the transmitter. This signal is modified with some gain, which for the theoretical purposes, I say gain. In every practical channel, this is going to be some form of attenuation, right? Some loss of energy. And the signal is also corrupted with some noise. And this is what comes at the output of the channel. So the model for the channel is this. It has some sort of attenuation, and it has noise that corrupts the signal. So this is my channel. In this case, R of t is going to be S times A times S of t plus N of t. Right? So that's the mathematical expression here that tells me how does the channel modify my signal. Here S of t, I should say transmitted signal. N of t is going to be noise. This A is going to be channel gain. And this R of t is received signal. And I purposely spell them out here because I'm going to be using the same notation for other channels, but I'm not going to define them over there. It's the same definition will hold. Now, this is the simplest of all the channels that I can have. What kind of distortion does this channel introduce to the signal? Can we enumerate what happens to the signal that makes R of t different than S of t? First thing is this A, right? So as the signal propagates through this channel, it gets attenuated. So there are two, I guess, the distortions here. First one is attenuation. What type of the distortion is this? Is this additive or non-additive distortion? It's a non-additive distortion because it's a multiplicative distortion. It multiplies your signal. So it's a non-additive. The second type of distortion here is the signal gets corrupted with noise. So this is additive noise. And this is an additive type of distortion, right? Because you have now the signal that is present in your output that was not present at the input, right? Here, when you have a multiplicative distortion, every frequency that you placed in the input actually comes at the output. It just might be attenuated, right? But here, in addition to that, you have some components of the output signal that didn't exist in the input itself. So what happens here? Let's just, so that we're clear what we're looking here, I'm just going to use this section of the board. Let's say you have, this is T, this is T. Now let's say the signal S of T looks somewhat like this. This is what I feed into the communication system. This is what I feed into the channel. So what comes at the output is the signal that is attenuated somewhat, so this is not going to be as large as this here. And also on the top of it, you're going to have this noise that is going to corrupt signal. So now this is presented to the receiver, and somehow receiver needs to look at this and say, oh, it was this that has been sent, right? So the receiver needs to do a lot of processing to undo even what is done by the simplest possible channel. Now, this is, as I said, the simplest channel. In many cases, it's the best case scenario, right? So when we analyze our communication systems, we're going to actually first try to benchmark their performance in this channel here. There's a special version of this channel where this noise has a properties of being Gaussian and white. And if that's the case, then we define something that we call AWGN. So the special version of this channel is, let me just put here, AWGN. So that stands for additive white Gaussian noise. And AWGN is a special version of this channel, and that's the one that we almost all the time consider as the first one when we benchmark the performance of a given communication system. We're going to spend the most time working in this channel because we're at the beginning, right? So we're going to try to understand what does this channel do to our signal and how we can send the signals through this type of channel. Okay, so the next type of channel is what we call linear time invariant filter channel. So this is two linear time invariant filter channel. The block diagram for this channel looks like this. You have, again, your input signal here, but then the channel acts as a filter that I'm going to specify through its impulse response here. And also, the signal is corrupted with the noise. So now, these two together make a channel. And this is your output signal. In this case, the output signal R of t is S of t in convolution with h of t plus n of t. Okay? In this expression, this star, as you probably know, indicates the convolution operator. In its expanded form, R of t can be written as integral when tau goes from minus infinity to plus infinity, S of tau, h of t minus tau, d tau, plus n of t, or, which is one of the theorems, these two are interchangeable, so I can have tau goes from minus infinity to plus infinity, S of t minus tau, h of tau, d tau plus n of t. Okay? So, so this channel, just like the previous one, introduces a set of distortions. Now let's take a look at what are the distortions that are introduced by this particular channel. First thing, so let me kind of enumerate distortion. Amplitude of the signals, amplitude of the signal components are changed. Also, the phase of the signal and then the third one is you still have additive noise. these two are, again, non-additive distortions. This is an additive distortion. Now, these two statements are somewhat ambiguous at this point, because some of you know them from earlier courses. But in this course, we actually shed a lot of light on what does this really mean. What I promised you here is that you're going to stop seeing the signals as their time domain representation most of the time, but you're actually going to see them as a whole bunch of sinusoidals that are lined up in a particular way to form this signal. And what this channel does here, it looks all of these individual sinusoidals and treats them in a different way. That's a fundamental difference between this channel and this channel. This channel would treat every sinusoidal the same way. It will attenuate every sinusoidal by the same amount. Here, the channel may prefer certain sinusoidals over the others, and that's that filtering aspect of the channels, because you remember what filters do, they amplify certain portions of spectrum and attenuate certain other portions of the spectrum. So that's the linear time invariant channel. This is actually more realistic channel. A lot of real channels behave like this. None of the channels behaves like a WGN over the entire frequency range. We can approximate it if the bandwidth of your signal is much smaller than a channel bandwidth, but this is kind of just a mathematical fiction. Some of the real channels may actually behave like this. And I'll go through some typical examples in just a second. So any questions on this channel? Right? So in this course, when I say, okay, let's look at the transmission through the linear time invariant channel, what we're actually going to do, we're going to say, here's the channel, it has this impulse response, and it has the noise with these particular characteristics, and then this will fit to this particular channel. The last channel that we're going to talk about is linear time variant channel. The model for this channel looks like this. This is your input. You still have an impulse response, h, but now it's h of t at some time tau, right? Some different time. And I'll explain this a little bit in more detail. And then inevitable noise added to the end to produce your R of t. So now this whole block makes a channel. Now, how is this different than this channel here? This one is, this channel here is the same regardless of when you look at it. If I transmit through this channel today and tomorrow, the impulse response of this channel will stay the same, right? So that's the time invariant piece of it. It means that the impulse response of the channel does not change over time. There are channels that have impulse response that are also linear filter channels, meaning that they can be modeled like this. But the impulse response changes over time, right? That's the time variability of this channel. Now, how do we calculate R of t in this particular case? The channel is still linear, therefore the convolution still holds, right? So I can calculate here R of t, but at some time tau is going to be equal to integral when mu goes from minus infinity to plus infinity, s of mu, h of t minus mu at a given tau d mu. Okay, so I have to now, mu is just a running dummy variable. It helps me do the integration. Here, what you have embedded is that if I take the same signal, s of t, and I feed it into this channel at two different times, tau, I'm going to get a different output, right? And the input-output relationship is still linear. It's still convolution. but the impulse response of the channel changes over time, and therefore, even the same input fed at two different times will give me different output. Okay? Now, this may seem a little bit, at least at this stage, without any examples, it may seem a little complicated, but you will see that this is not uncommon. As a matter of fact, some of the most common channels that we use exhibit this kind of property. So let's first look at an example of the linear time invariant channel, and then look at the example of the linear time invariant, the time variant channel. So example 1, this is linear time invariant channel. The most common linear time invariant channels have transfer characteristics, which is your age of f, which you know is I guess Fourier transform of age of t, magnitude of f. That looks somewhat like this. This is your typical low-pass filtering channel. This fits, this mathematical model describes in a pretty good accuracy all of your electrical wireline channels. If you look at twisted pair, it has the transfer characteristics that is somewhat like this. If you look at the coaxial cable or even waveguide, they behave somewhat like this. We usually talk about what is called cutoff frequency, FC, cutoff frequency, and this is, you know, minus 3 dB or 1 over square root of 2 here, and some numbers so that you kind of get some idea. FC is around 100 kilohertz for twisted pair. FC is around 100, or I should say up to 100 megahertz for coaxial cable. And can be, let's say, up to 100 gigahertz for waveguide. Now, these numbers are not very accurate. They're just to give you orders of magnitude, right? You cannot really have, or it would be really, really sophisticated waveguide to get to 100 gigahertz. But there can be waveguides to, let's say, 30, 40, 50, even 60 gigahertz, right? And I kind of rounded these so that you can remember them easily. So about 100 kilohertz, that's what you get from the twisted pair. You know, 100 megahertz is what you can get out of the coaxial cable, and 100 gigahertz out of the waveguide. Right? Okay, so that's an example. And then one thing about it is, you know, if I have a twisted pair and I measure this characteristics of a twisted pair, it's not going to change much over time, right? It may change, you know, due to the aging or somebody stepped on it or something like that. But the scale of these changes, time scale of these changes, is going to far exceed the length of any communication that I'm going to have here, right? If I communicate, let's say, over 2 minutes, but for this cable to change, it will take 20 years, right? So the changes over the duration of the communications are going to be negligible. That's why the model where I model this channel as a time invariant filter is a pretty good one. Example 2. This is linear time variant channel. An example of that is your wireless communication channel. Okay. So how does the channel look in this particular case? Well, here's what you have. You have your transmitter from which you're going to send your signal, and then you're going to have your receiver for, just to make sure that we understand that there's mobility involved here. There's some vehicle here moving around. Let's say this is a radio broadcast, and this is my car here receiving the signal. Now the signal gets to this antenna several ways. There's a wave that travels directly. Then there's a wave that reflects from this building. There's a wave that reflects from the ground. There's a wave that reflects from far away here and reaches this particular channel. So now, think about what happens if I send a pulse here. And ideally, theoretically, if I send an impulse, right? Well, there will be a several replica of the signal that I have sent that are reaching my receiver, right? So let's take a look at, now this is time t. And let's say this is my impulse response at some time tau. And I'm going to let tau axis run like this. So this is, let's say I send a pulse now, and I'm just going to simplify it, assuming that I'm sending an impulse, and I'm going to put what comes at the output. Let's say I get the first reflection, that's my direct wave. Then there is this guy here that comes a little bit after, but it's somewhat attenuated. There's this guy that comes quite a bit after, attenuated even more. And there's this one that comes, here, right? So I have 4 responses to my signal impulse that I have sent over the channel. Now, I let time go by, and then I send another impulse. So what happens in this case? Maybe this one comes here, there's another one, there are 3 more here that are coming, and so on, right? So you can now see that this is here tau equal to 0, tau equal to tau 1, tau equal to tau 2, and so on. So you can see now that if I send an impulse at different times, I'm going to have a different channel, different impulse response, right? And because of the mobility of the receiver, the impulse response of the channel changes all the time, right? Even, you can see, when we talk about wireless channel, even if this receiver stands still, the environment itself is not still, right? So maybe there's a reflection here that came from another vehicle. Even if this one stands still, the reflection from this guy is going to change over time. So the point here is that in a wireless environment, your channel is changing constantly, and you have to be able to accommodate for that. Now think about how demanding the task is. You're sending a signal into the channel that can change anytime, right? And it does change all the time, right? So now you have to be very smart to adapt your transmission and reception so that no matter what happens to the signal, your receiver has enough knowledge to undo the effects of the channel, right? And that's what happens every time you pick up your cell phone to communicate over this channel. There are other types of channel that we didn't cover here, right? Just let me know them. All the channels that we have covered are so-called linear channels. Channel is linear if it's described through linear system theory, right? If the superposition holds, convolution holds, I put 2 signals at the input, I expect to see 2 signals at the output, they're not mixing together. Majority of the channels, due to the nonlinear devices that you have along the way, so all of your power amplifiers, mixers, all of those things, would actually introduce some sort of nonlinearity. And what happens is, the signal now gets additional distortion, which results from that, where there's a mixing in the spectral components. We're not going to talk about it in this course, just be aware. But you can have, again, nonlinear channels that are time invariant, nonlinear channels that are variant, and so on. And usually, when we analyze those, it gets pretty complicated pretty fast because, and to be honest with you, we don't really have good math to describe these channels, and we deal with them on a case-by-case basis. We talk about these channels a lot when we talk about, in a course that we have here that's called Wireless Design Concepts, where we actually talk about properties of the power amplifiers and the distortion that they introduce into the signal. So, any questions about any of this? Okay, so where we're going to go from here is, as I said earlier, this is the only time where we're going to talk about the channels. We're going to from now on, use appropriate channel model to deal with transmission. And we're going to focus, transmission and reception, and we're going to focus on two basic blocks, transmitter and the receiver. But before we go there, we'll have to actually address the properties of the signal and develop some math that will help us understand how do these signals actually propagate through channels? What actually happens? And for that, we need to kind of review some basics in Fourier analysis. So we're a little bit early for this first section, so let's stop and give you guys a break, 15-minute break, and then we'll come back.